So I thought I'd go through some questions with you from your textbook review for chapter 4 on scale factor and similarity. So what I've done, I'm not going to go through every question, but what I've kind of picked out are the questions that I find students tend to get stuck on or just sort of aren't sure about, so they need additional support or just want to see how maybe I would set up my solution. All right, so let's start with number 5. They give you the shape and two questions tied to it actually. So they want you to redraw it with a scale factor of 2. So you'll notice that I've pointed out if your scale factor is bigger than 1, that's an enlargement. Okay, so I want to take this shape and kind of think about like enlarging it like that. And then question B is a scale factor of a half. Well, reminder, if your scale factor is less than 1, we consider that a reduction. So that would be like me taking this picture and then sort of squishing it, so making it smaller. Okay, so you'll notice beside I already have my grid that I can fill in. So I'll start with the enlargement with the scale factor of 2. And you'll notice, so I kind of identified this is a length of 1, that's a length of 1. This length right here, okay, I'm just going to say that it's basically a diagonal going through one square. All right, because actually technically the length isn't equal to 1. So I'll just say this is going through one square. So you'll also notice that I have a dot set already. So all I'm going to do is I'm going to imagine drawing this dot on my new enlargement over here. So I'm going to put it right here. All right, now if I follow, this one originally was to go 1 unit, but if it's a scale factor of 2, you're going to double that. So if this was 1, now I have to go down 1, 2, right? So now I'm here, and then I'll keep going. So I originally went across 1, but I have to double that. So go across 1, 2, I'll get that point there. So now I'm here. So here's the trickier part. I'm going to just think about that from here to here. I went through one square in a diagonal motion. So then from this point, I'll imagine going through one square, but it's been doubled. So I'll go through 2 squares. So I'll end up here. That's this point. And I'll just keep going. So 1, 2, that gets me here, back 2, then I'm here, down 2, and here, again through 2, gets me here, through 2, gets me here, up 2, I'm right here, across 2, right here, through 2, right here, and I'll be here, go back 2, go up 2, through 2, and then you'll notice we end up back where we started. So you'll notice I've now connected all of my dots that I drew out with the enlargement scale factor of 2. You'll notice my lines are not the best. Okay, you guys know me. I still haven't figured out necessarily how to draw nice straight lines with this program. It just never seems to work well. So please keep in mind, if you guys were drawing this yourselves, the expectation would be to use a ruler or a straight edge of some sort. All right, so again, what happened here? All of these lengths that were 1, you'll notice have now doubled. So that's 2, that's 2. And like I said, this one, for example, that went through one square has now gone through 1, 2 squares, right? Then question B, this was reduction. So as you can see, there's my shape that's been reduced. And again, what I did, I started right here. It doesn't matter where you start your shape. You could start here, you could start it down there, as long as you know that you can fit it on your grid. And then this time, so instead of going down 1, this would be, let's zoom in. So this would actually be a length of a half. This is a length of a half. And then that diagonal, sort of the trickier part, you'll notice before it went through a full square, but now it's only going through half of a square. Right? So that would be my reduction with a scale factor of 0.5. So number 9 talks about an actual CD jewel case measuring 14.3 centimeters. Now, I know the joke I kind of made in notes too is who buys CDs nowadays, but it works for us just to practice the concept of scale factor. So we want to determine the scale factor used to create the image. You'll notice I crossed off image and just wrote down diagram. So when they talk about the image length, that's referring also to the diagram length. And most of the time, the formula we used, we talked about diagram compared to actual. So as a reminder, scale factor, you can find it by taking diagram measurement divided by actual measurement. The key with this though, units have to match. So I'm going to check diagram measurement is 2.2 centimeters, actual is 14.3, so it looks pretty good. So then all I'm going to do is fill in my values. So I'll go 2.2 divided by 14.3. You can drop the units because scale factor actually doesn't have units if you're writing it in this form. And then if I divide those two, okay, the question doesn't tell us what to round to, so I'm going to keep 4, so it'd be 0.1538. Okay, so that would be the scale factor. Now, that scale factor is definitely less than 1, so it makes sense that the original has been reduced down. Okay, so this should be smaller. And then in your textbook, if you check the solution, they ended up writing it as a fraction, and I think they said that it was 2/13. So let me double check that. 2 divided by 13. Yeah. Okay, so they've written it as fraction. As long as you're getting the decimal, I would be happy here. On your unit assessment, I'll specify if I want it as a decimal or as a fraction. Okay, so if you're getting the decimal format, then you're good to go. Okay, number 10, determine the actual length of each object from its scale diagram. So there were 2 questions. I'll just do 1 question though. So they give you a spoon. They show you that the diagram length is 3.5 centimeters. Right? It wouldn't make sense to have a spoon that small, unless maybe it's for like dolls or something. But anyway, so the 3.5 is our diagram. We'll highlight that. So that's diagram length. And then they tell you the scale is 1 to 4. Right? Now, you want to be careful. When we're going to use the scale in this formula, okay, when we're trying to solve the question, it's probably better to switch this. Remember I talked about changing it to a decimal or a fraction. So you could use 1/4, right? That's what that means. Or you could also use the decimal format, 0.25, right? So let's plug in our values, see what happens. So our diagram length was 3.5. And again, I'm going to just leave out the units while I do the calculation, and then I'll make sure I have the correct ones with my final answer. So we are dividing that by our scale, use the fraction or the decimal. I'm going to use the decimal for this question, so 0.25. So then the actual length makes sense. It should be a bigger number. Okay, so you'll have 14, and now I would include my units. So we would say that the actual is 14 centimeters. Okay, so again, when you get an answer, think about it. Well, if the actual length is 14 centimeters, and we're saying our scale factor was 1/4, right, or 0.25, which is less than 1, this scale factor is going to be reducing the actual. So it makes sense that if it was 14, it's now been reduced to 3.5. Okay, so number 11 talks about you have a scale for an image of a tower, and you're told 1 centimeter represents 12.5 meters. You're given the actual measurement, and they want you to find the height on the drawing. So you'll notice I highlighted the information tied to the scale in yellow, actuals in blue, and then we were trying to find the drawing length. But you got to be careful. So if you want to use these formulas, your units, you want to make them match. Okay, so I have 1 centimeter here, but I have 12.5 meters. So keep in mind, right, 12.5 meters would be the same thing as 12.5 times 100 centimeters, because there's 100 centimeters in 1 meter. So we could say that 12.5 meters is the same thing as 1,250 centimeters. So I'm actually going to go back to my question. I'm going to cross this out and say 1,250 centimeters. Okay, so now they're matching. So then in my formula, the actual length, I know that this has a value of 108.75 meters. Okay, so this is 108.75 meters. But again, we got an issue there. That's not in centimeters. So 108.75 meters, if I times that by 100, that would give me 10,875 centimeters. So I'll also cross this out. So I'll say that's like 10,875 centimeters. Okay, because if my scale is going to be centimeters, I want this to also be centimeters, right? So I'll fill in, then our actual length is 10,875 centimeters. I'm going to drop the units, times my scale factor. Okay, well, the scale factor is 1 centimeter represents 1,250. Now, I would want that as a fraction or decimal, so I'll put it as a fraction format. That's 1 centimeter represents 1,250. Right, I'm going to multiply those together. Okay, and I'm going to find that the drawing length then would be 8.7 centimeters. So a bit of a tricky question. There's kind of a lot going on there, but because you have centimeters and meters mentioned, you want to choose to switch one to either, or sorry, both of them to either centimeters or both of them to either meters. Now, you could answer this question in meters, but probably makes more sense to talk about a drawing length in centimeters than a drawing length in meters. All right, question number 12. Similar to number 11, we're going to have to watch our units. So a highway is 600 kilometers in length. If the length of the highway on a map is 6 centimeters, what is the scale factor? And they do give you a hint. So 1 kilometer would be the same thing as 100,000 centimeters. So we're going to make sure that everything is in terms of centimeters. Okay, so the length of the highway on the map is 8 centimeters. Right, so that's our diagram length. This is fine. That's going to be going there. But the actual is in kilometers. So if I know that 1 kilometer is 100,000 centimeters, what I'm going to do is go, well, 600 times 100,000 centimeters is going to be, there should be 1, 2, 3, 4, 5, 6, 7 zeros. So that would be 1, 2, 3, 4, 5, 6, 7. So 600 kilometers would be the same thing as you saying you had 60 million centimeters. Right, so we're going to use that for a formula. So this is going to go here. Okay, so our scale factor then, we would say diagram, which is 6, divided by that 60 million, right? You'll notice, right, this is in fraction format. And if we divided that, so 6 divided by 60 million, it's a pretty small number. So we could reduce this down as a fraction. So this would be like 1, because you could divide the top and bottom by 6, over 10 million. Okay, so the scale factor is basically 1 centimeter on this drawing is representing 10 million centimeters of the actual length. All right, moving on to question 13, I believe. Yeah. Okay, so the question asks you, are these triangles similar, and explain. So reminder, for triangles to be similar, their corresponding angles have to be the same, so they have to be equal, and the corresponding sides have to be proportionate, right? Now, the way that these diagrams are set up, so I have this big triangle, small triangle, they are saying like that A corresponds to D, F corresponds to C, and E corresponds to B. So what I've done then is I've highlighted the sides that would be corresponding to each other. Okay, so for example, I started with the shortest side. I noticed it was 12 here. Well, the shortest side here is 2.4. So those are corresponding, highlighted in yellow. Then if you look at the longest side, this one's 19.2, this one's 4.1. So those are corresponding. And then process of elimination, the numbers in green. Okay, now I don't have any angles, so that's not going to help me prove it. But I can look at what happens when I relate their sides. So I'm going to start with the big triangle first compared to the small. Only reason is I saw the big first, then the small. Again, you can flip these. Okay, so let's plug in some numbers. So on the big triangle, I have the 19.2. So I have it all color coded for you guys. Comparing that to the 4.1. Then I have, go back to the big triangle, I'm comparing 12 to the 2.4. And then I'm comparing the 15 to the 3. All right, now this is a bit tougher to see, so I'm going to actually divide these. So 19.2 divided by 4.1. Okay, and again, probably a good idea, keep minimum 3. So So I'm going to write it as 4.68, and actually I'll go 4, so 29. Okay, check the next one, 12 divided by 2.4. Whoop, we actually got a nice number there, that's 5. So right away, these are not the same. Okay, yes, you could round this and say it's 5, but when you're talking about similar triangles, they have to be exactly the same. Okay, so you can't round and then assume that they are the same length. So this is failing right now, but let's just double check. Well, I know 15 divided by 3 would be 5. Okay, so then I would say, because these are not the same, so sides are not proportionate. So not similar triangles. So we've proven that they cannot be similar. Okay, question number 14. So still tied to similar triangles. This is the picture that you're given. Okay, so mine looks a little busy. What I did is I imagined if I took this small triangle and then kind of like pulled it apart, this is the same thing, okay, just rewritten. So there's a side of 11, 11. We're trying to figure out the length of x. So I'm gonna like highlight that in yellow. And then I highlighted this in pink, and then I realized it kind of just gets super busy. So again, I just drew it out again to make it a little bit easier to read. But what you got to be careful about, for example, this length here, okay, it's 11, but plus the 25.3. So that's why I'm saying this whole length is 36.3. Same thing here, it's 11 plus the 25.3, okay? So once I do that, I can kind of ignore the original and just focus on small versus big. Okay, so for me to solve this, I'm going to go small, comparing it to the big. The reason why I put small on top is I'm trying to solve for that x and all corresponding. So this side x is compared to this 33. So those would be my yellow sides. So x compared to 33. And then it doesn't matter, what other color could I use here? No, it's like pinky. These are both the same. So I'll go back, take this 11, compare it to the 36.3. Maybe not the best color, but it'll work. So the 11's on top, 36.3. Wait, I apologize for my interruption there. One of my kids had to ask me a question. So the joys of teaching from home. All right, so we're trying to solve for x. So we set up our proportion statement. I am now going to do half the cross multiplication. I can do that because my unknown is in the top. So it could be in the top on the left or the right, and that saves me from only having to do half of it. If you want to show the full cross multiplication, you go right ahead. Right, so I'm going to go 11 times 33, and then we're going to divide that by 36.3. Well, here's what happens. You get 363 on top, divided by 36.3. You end up with finding that x will equal 10. Okay, moving on. I apologize, I think I did question 15. Yep, okay. So 15, given that triangle GHI is similar to triangle KLM, what is the length of side IG? So they're representing that by an X. Remember, the way this is labeled, that means then that G has to be the same as K, H has to be the same as L, and I has to be the same as M. Okay, so I've already kind of labeled some corresponding sides. So I know that GI corresponds to KM, so I highlighted it in green, and then HG corresponds to LK, so I highlighted those in blue. All right, so setting up my proportion statement, I am going to compare, so X compared to 10.5, and I'm going to set it equal to, now because I have small on top, go back to the small, 4 will go on top, and I'm comparing that to the 14. Okay, you're going to cross multiply, so we will have X is equal to 4 times 10.5 divided by 14. So that would be like us having 42 divided by 14. And we would say that that answer would be 3. Okay, question 16. So this one is determine if the two polynomials are similar. Different question than the last two because now we have a polynomial, not a triangle. So this was tied to section 4.4. It has the exact same characteristics though. So if they're supposed to be similar, your angles have to be equal. So corresponding angles have to be equal and the corresponding sides have to be proportionate to each other. And again, the way the diagram is laid out, you are to assume that P would correspond to A, angle S would correspond to D, etc. So I've already highlighted the sides that are corresponding to each other. Okay, so this 3.5 would correspond to this 1.5. So that's what I'm going to check. So if I go 3.5 and I see how it's connected to 1.5, that's my yellow sides, is it the same value for the green, which is 3, compared to 1.3? And is that also the same as the blue, so 3 compared to 1.3? Well, I know right away these will be the same. They're the same numbers. And then is it the same as the pink, the 1.8, compared to the 0.8? Right? So I would take my calculator, 3.5 divided by 1.5. You're going to get 2.3333. So I'm trying to say, is that equal to 3 divided by 1.3? Well, this time I get 2.3077. I rounded that to 4 decimal places. I know this will match. It's the exact same fraction. So 3077. And then the last point, so the last one, 1.8 divided by 0.8 is 2.25. Okay, so are these polygons similar? The answer is no, right? This number is not matching this number doesn't match that number doesn't match that number, all right? So again, you gotta be careful because had you rounded these to 1 decimal place, this would be 2.3, 2.3, 2.3, 2.3, then you might be inclined to say they're similar, but when you're trying to prove whether or not shapes are similar, you have to make sure that you're not rounding because then you might get an incorrect answer. So I would say these are not similar because corresponding sides are not proportional. Right? Okay, last one. So tied to similar polygons again, you have the pentagons D, E, F, G, H, J, K, L, M, N, and they're telling you they are similar. So the way this is listed, that means these angles would match, those would match, those would match, those match, oops, and those match. Okay, so we're trying to determine the missing side lengths. There's 2 of them. We want to find X and we want to find Y. And so I label it small, big. Okay, I already highlighted the sides that are related to each other. So I'm going to start with the X. So if I want to solve for X, I highlighted it in yellow. So I'm comparing X to 17.3. And then I can't use the green because I don't know what Y is, but I could use the blue or I could use the pink. It doesn't matter. So for this one, I'll use the blue. I'm going to compare 9.6. So compare the 9.6 from here to the 23 from the big. Okay, we're going to cross multiply. So 9.6 times 7.3, divide that by 23. I'll do it all in one step. It says to the nearest tenth, so we would say X would be 7.2. Okay, so I know what this one is now. Then let's do Y. So I'm comparing Y, which is green, to this green length, which is 23. And maybe this time I will use the pink corresponding sides. So we can compare the 4.8. Reminder, these have to both come from the small. These have to both come from the big because the way I set it up. So I compare the 4.8 to the 11.5. Again, cross multiply. Y will be 4.8 times 23 over 11.5. and you get your answer, which would be 9.6. All right, so tons of examples to hopefully help you guys out with your test review, as well as your unit assessment that I will be posting for you tomorrow. Keep in mind, so some of these questions, I didn't necessarily put a concluding sentence or a final statement. Whenever it is a word problem, you should state it as a final, state it using a final sentence. Just I was trying to save you guys some time from having to watch a video that got too long. Anyways, hope you guys have a wonderful day. And don't forget, if you're stuck, please, please, please email me. Also, feel free to just email me, say hi. And yeah, have yourselves a wonderful day.